So welcome to the last week of our course. We started to study homogeneous spaces. Last time, so we'll finish these topics. First, the definition is that homogeneous space is some L with some action, say left, also right can be, which has the property that you can go from any point to any other point. So M equals just one orbit. So each orbit is automatically a homogeneous space by definition. And this way of acting is called transitive action. Transitive action means that any 2 points are mutually reachable by some G. Yes? That if you take any 2 points on your M, there exists G which connects them. But we already studied, I will repeat the computation because it is very short and very important, that it doesn't mean that 2 points can be mutually connected by a unique element. Imagine that we have two group elements with this property that acting by this M0, you go to some M, which is the same for two group elements. Then, by acting G1 to minus 1 on this equation, we obtain that M0 is G1 to minus 1 G2 acting on M0. And it means that this H is from stabilizer of M0, which is a subgroup of G. Yes. So it means that G2 is G1H, and this is any element from H equals GM0. So it means that not only G goes from M0 to M, but also any GH does the same job. Yes, for any H which leaves this M0 stable here. So now remember that we constructed such nice picture. G over H. It was also, I think, last lecture, maybe sooner even. Here is H, here is some GH, here is something called G, and here say E, because unit element of the group is in this any subgroup. Here is somewhere G. Now what is if H in this construction is GM0 on our M LG, somewhere here, this means that there is a bijection between points of M and these left cosets. These are called left cosets. Yes, because this computation showed that all group elements which move M0 to M are exactly left coset on this picture. Yes, so we have a bijection of all these group elements and this point. You go from here to here by any GH. So by any point from left coset on this picture. So this is very important that we can somehow parameterize elements of this homogeneous space, not by group elements, but by left cosets created from group elements in general. Yes. Once again, if we fix this M0, now it is important that on our homogeneous space, we should fix single point, any one. And now we can parameterize all other points, including this M0, of course, by group elements, but not single group element parameterizes this M, but whole left coset parameterized. So it is quite convenient to write it as a mapping now M to G over H, which is here, because instead of using to parameterize the point, all these points, we will parameterize it by a single point down here. Yes, there is a projection, so-called. It was already explained, everything here, including the fact that it is an example of something which is called fiber bundle. Yes, that there are fibers, and all fibers are bijective mutually, and there is a projection. So, because there is a bijection now between points of M and these sets, so it is much more convenient to think that it is a bijection between points here and this point, just. So we introduce now this mapping, that this M goes to this G. Yes, this M to this G. So M, which is GM0, because any M here should be GM0, because it is homogeneous space. So any point is reachable by some group element. So it can be written like that, and it goes to G. Yes, or that Cm equals psi M, psi GM0 is by definition this G. Now, is it well-defined mapping? Yes, because here is a freedom of inserting any H. Because H acting on M0 is just M0. H is from stabilizer of M0. But here is also a freedom of H. So it does not depend on representative. It is well defined. Potentially, it is dangerous, this mapping, that it depends on representatives. But we see from two sides that the left-hand side, here, if you put instead of particular G, you can put GH. Yes? And nothing bad happens because H on M0 is just M0. And here, it is from the definition of left coset that the class of G is the same thing like the class of GH. It is more or less definition of a left coset. Yeah, that it is GH. So we see that there is a very natural mapping whenever you have action, whenever we have a homogeneous space with some action. So if you compute a stabilizer of any point, this was arbitrary point, and call it H, this stabilizer, then you see that there is a natural bijection mapping. Yes, this is bijection. Natural bijection mapping between your homogeneous space and some G over H which was defined before. What is it? It is here. And now it turns out that it is more than just bijection, that it has important algebraic properties, namely that this is isomorphism of homogeneous spaces. So we will introduce this concept. Isomorphism of homogeneous spaces or equivalence. Imagine we have two homogeneous spaces, one of them M1 with left action, say LG1, and another one M2 and LG number 2 here acting, yes? Now the isomorphism that it call some F is a mapping which is first bijection, and then second it commutes with the actions or it is equivariant we already had this concept. I don't know whether you remember when we studied groups, representation of groups, and we introduced a concept of intertwining operators there. Yes. So also intertwining is sometimes used. Intertwining. So what does it mean that I will not write here these actions, but M1 to M2, here is F, here is action, LG number 1, on M1, here is M2, action LG number 2, and here is F again. That means, what does it mean to commute? It is the property that this diagram is commutative, that F followed by LG2 equals F LG1. So it doesn't matter whether you go this way or this way on the diagram. And what does it mean? That this F knows pretty well that there is an action here and there is an action here, and it respects it. That it doesn't matter whether you first go to M2 and then act by Lie group element G according to L2 recipe, or first act directly here by group element G according to this rule, and then do the map. Yes. So there is some commutation of mapping F and acting by the group. By the actions, now are two actions. If you act by group here, you should do it according to LG1 recipe, and if you act by the group element G here, you should act according to this rule. So this says that it doesn't depend on the order in which you do it. So this F knows pretty well that there are two actions, and F decides to be nice with respect to these two actions in this way. So if it is bijection and has this property, actually you can forget about one of these objects. If you want to do anything with M1, L1, G, you can replace it by work on this, because you do not lose anything if you think it over. Yes? Everything can be done either here or here, so you can forget about one piece, because they are isomorphic in completely equivalent. And now we have an example of this situation. By the way, this intertwining we had, as I mentioned, in representations, it was something like here, but in the linear context, these were linear spaces and linear operators. These actions were representations, and these M1 and M2 were linear spaces, where the representations work. So then it was called intertwining operator. It is not an operator, but some mapping, and it is general, not restricted to linear case. Yes. Now come back and notice that we have a very natural bijection between one homogeneous space and other homogeneous space. In this homogeneous space, we have action some LG, it is written here, and here we have some other action called LG, which was introduced on the last lecture. And the claim is that this psi is isomorphism of these two homogeneous spaces. Psi is isomorphism of the two homogeneous spaces. The given one, any one, remember that this is any given homogeneous space by some points and by the rule how a group acts. Two homogeneous spaces, this and G over H, where H is GM0. So last lecture we constructed this G over H and we proved that it is a homogeneous space. Remember that the action is this action where here this action was given by this simple rule. And we proved that it is well-defined rule. Yes, that this element acts on some element on G over H in this way that you find any representative of this class, act by left translation, and then project it down. It is said here. So what we are to prove, first that it is a bijection, number one. I already explained it. And now that it commutes with our two actions, so that it commutes with what? First psi, where is the picture? I will write the picture here, complete that M psi goes to G over H. Once again, psi, and here is this arbitrary left action, and here is this left action here. So the claim is that this diagram is commutative, or that first psi, then LG, this LG, which is left action on G on H, is the same like this. And it is very trivial proof. Apply it on any, for example, which one? This one. Psi should be applied to some M, which is, say, GM0. Because any M is some group element applied on M0. So psi applied, it is LG on what? Psi applied on something, it is here, is the class of this group element. And by this definition, it is G0. And you can now apply the right-hand side on this same element and show easily it is just 2 or 3 equality signs that it is the same. Yes? So the definition of isomorphism is simple and natural, and the proof of this theorem is simple and natural. And what is the meaning of this claim, this theorem? Is that actually there are no other homogeneous spaces than G over H. Because this was arbitrary homogeneous space. And we found isomorphism to a homogeneous space of the structure G over H. And it is isomorphism, so any homogeneous space is isomorphic to some G over H. So if you forget about homogeneous space and remember just G over H homogeneous spaces, you do nothing bad. Because there are no other homogeneous spaces as G over H by constructed directly in terms of group. Yes? So some examples. We already had several homogeneous spaces, like sphere, for example. You remember that we computed orbits. And whenever we computed some orbit, we already get homogeneous space, because each orbit is a homogeneous space from definition. So which orbits we did compute? We computed some orbits which were spheres, maybe you remember. Interesting and important. That when we introduced the concept of action, we studied action of SO, say SO3 on R3. Actually, we did it, I think, for N. Like that matrix X goes to X, or AX. And then we studied that what about the orbit of North Pole, this North Pole, of the future orbit. Yes, the orbit is like that. This two-dimensional sphere. Here is the North Pole. And we learned that when we act on this North Pole by any group element from SO3 in this way, we can achieve any other point on this sphere. So the sphere is the orbit. So orbit of the North Pole is this S2. So we have an example of homogeneous space, nice homogeneous space, sphere S2 embedded in R3. Now we know from this that each homogeneous space, that means also this sphere, is isomorphic to some G over H. So now we want to construct this G and this H and to write a scientific result that it is isomorphic to some G over H. So what G? It is this G which acts here transitively. So it is G is SO3. And what is H? We learned that choose any point on your sphere, so for example this N, and find, in general it is a stabilizer of some M0. So what is it? It is stabilizer of SO3 of the north pole. So it is some subgroup of SO3 which has all these elements which leave this north pole intact. And we computed it, maybe you remember, that for n dimensions, we computed that the structure is like that, where this was SON, and this was from SON minus 1. And this can be bijectively mapped on these B's, because only B carries some information in this group element. So group elements of this structure form a subgroup isomorphic to SON minus 1. Yes. Subgroup isomorphic to SON minus 1. So here our H is SO2 as a subgroup of SO3. Yes, so we have B here, 2 zeros and 1, and it is isomorphic to SO2. But it is not just SO2 element, 2 by 2 matrix, it is 3 by 3 matrix, because it should be subgroup of SO3. Yes? So it looks like that. But it is fully given by this 2 by 2 matrix. So what is our scientific result? That the sphere S2 is SO3 over SO2. Yes? And in general, by this construction, have a look to computation of this stabilizer. In general, that Sn is SON over SON minus 1. So this homogeneous space is isomorphic to homogeneous space, which is Sn with standard action multiplication by SON matrices on columns. And still one maybe useful example, that we can generate spheres also in terms of complex matrices. So again, example that now let G be SUN, and it acts on Cn. Yes, columns are multiplied by matrices from SUN. Now, if you compute what happens when you act on 0, 0, 1, which is, so this acts on Cn. It is now treated as an Cn element. That means that they are complex numbers, but happily they are real. Yes, but they could be complex numbers. And this goes to what? If you multiply 0, 0, 0, 1, we already did it several times, you obtain the last column of the matrix. So it is A11, A1n. But now remember that this A is from SUN, so A plus A equals A plus equals 1, and determinant of A is number 1. Yes. And these equalities say something similar like with transposed elements for SON, that all rows and all columns form orthonormal bases first, and together with this that they form right-handed orthonormal bases. For now, it is now important that this last column, it was here, yes, it came from here. It is orthonormal, it is a normalized vector, because it is a member of orthonormal bases. So what does it mean? That A11 complex conjugated plus A1n complex conjugated is 1. But they are complex numbers. So if, say, A11 is A plus IB, this is A squared plus B squared. And something similar for all K in this sum. So altogether, we have sum of, say what? C squared, 2n pieces equals to 1. Because 2 pieces from each term. And what does it mean? That it is a sphere in R2n. So we obtain sphere S2n minus 1 in either R2n or Cn. So each Cn space can be treated as real space R2n. And because this condition that this column is normalized to unity in combination that it is complex, it means that sum of several squares equals to 1. That means we have a sphere. And how many these squares are there? 2n squares. So the starting space is R2n, this Cn, and we have the sphere S2n minus 1 inside this Cn. So we see that we have another sphere as a homogeneous space, as an orbit. This is an orbit of this point. So orbit of 0, 0, 0, 1 with respect to this action is S2n minus 1. And now we want also to write it as some G over H, this orbit, this homogeneous space. So we have to find what is stabilizer of this point. And this is practically the same story. That stabilizer of this, do it yourself. It is just complex version of something which we already did when we try to find stabilizer of this structure. So it is some B001. This is from SUN, and computation shows that this is from SUN minus 1. That the stabilizer looks like that for this particular point. It is something like North Pole on the sphere. So we can write the result that S2n minus 1 is a homogeneous space SUN over SUN n minus 1. Yes, something like here. So, of course, this sphere can also be written like homogeneous space of orthogonal groups, but we see that also homogeneous space created from some unitary group gives the same homogeneous space. But this construction doesn't give you any dimension of sphere, but only 2n minus 1, which is odd dimension. Here is for any dimension. Okay. So now we also see some fact that after these two examples, some general properties, and then also example that how big are homogeneous spaces, so to speak. So any homogeneous space is G over H. Yes, and in the sense that is isomorphic too. This is sometimes called canonical homogeneous space, this G over H. So we see that any given homogeneous space is isomorphic to a canonical homogeneous space, some G over H. Now, the picture for G over H, we know that is that G, and here is G over H, this fiber bundle approach, so to speak. So what is the tendency? If this H is bigger and bigger and bigger, what is the tendency that what is the resulting G over H? Bigger or small when H goes to be bigger? H is here. Here are all group elements. H is here. So if H is bigger, what is the tendency of G over H? Bigger or smaller, or nothing? Smaller, yes, because more elements are in each fiber. So H goes bigger, G over H goes smaller, because the number of elements is the same still. So now there is the biggest subgroup and the smallest subgroup. So there are some limits for each homogeneous space. The biggest subgroups of any G is the G itself, and the smallest is just unit element. So there are some boundaries that G over unit element and G over G. What if, so it means that this is our H and this is our H, yes? So this is the biggest one, and it is like G. It is like something denoted like a point. Because if you have your subgroup G itself, this picture looks like nothing but one big H, yes? And just one point down. It is like this, that this is G equal to H, and here is a point G over G. This picture shrinks to this picture. And what about G equal just E? It is another funny picture, that here is G and here is G over E. Yes, that over G, you have just G and nothing more. Because this fiber is constructed out of GH element, and now the only H is E. So here is just GE and nothing more. So there are two extremes. This is okay, this is called trivial, something that you have action on one point which is trivial. It doesn't move the point, yes? But this is more interesting in a sense, and it is called principal homogeneous space. So the principal homogeneous space so this is G over H. You see that there is a bijection between G and G over H in this case, that the homogeneous space is as big as G. There is bijection from your homogeneous space to the G or backwards. But it is not the same thing, in spite that you have a bijection. What is not, there are different algebraic structure on these spaces. Here, on G, you have group multiplication and inverse and all that. But on homogeneous space, you cannot multiply two elements. In spite that it is as big as G, you cannot multiply elements of the principal homogeneous space. You can just act on these elements by group elements. This is the structure. It is also interesting structure, but different than the structure of the group. So, nice example is the one which was already mentioned here. Example, EL is a principal homogeneous space of GL and R. Do you remember this space? It is the space of all bases in linear space L. This is a linear space, and they are bases in L. So some element E1, En is from EL, and the action is EA goes to RAE, AAB, EB. It was already mentioned and discussed. That's why I just put it shortly and remember that something like this was already mentioned. We studied it a little bit, this action, and we came to conclusion that it is free and transitive. So it is a homogeneous space, and it is actually the largest homogeneous space of GL and R, which is in bijection with GL and R itself. Here is the bijection that you fix some bases, and then you have bijection to group elements, to A's, matrices A's, that each other basis is A applied on this basis which was chosen. But remember that this choice was arbitrary. So the bijection is not canonical. Because if the bijection were canonical, then we could also multiply bases. But we cannot multiply bases. There is nothing like the group multiplication of one basis multiplied by other bases. It is nonsense. It cannot be invented. Or inverse basis, yes, something like that. Because this bijection depends on the reference basis, which is arbitrary. So it is non-canonical bijection, and it is this EL is not a group, but it is just a principal homogeneous space of this group. It is very important. This space comes to a very important manifold in which, or in terms of which, a lot of interesting things can be studied, which is studied in 1 year from now, or more than 1 year, and it is called frame bundle. The concept of frame bundle is based on this concept. So it is very important. And in the context of the frame bundle, it is very important to realize that some fibers which are there are not groups, but they are homogeneous spaces, just principal homogeneous spaces. They look like groups, but they are not groups. Okay, now we go on to a situation that in which case we can make from this GH a group. Now the status of this G over H is that it is a homogeneous space, not a group. And in spite of this, it is very interesting. Yes. So in general, G over H is a homogeneous space for G, not a group. So we didn't study how to multiply two elements here, G and some G primed. But we can try to do it, and we will see that sometimes it is possible, but contrary to this case, H should have some property. Up to now, for homogeneous space, H is arbitrary subgroup. But if H is not arbitrary subgroup by some subgroup which has some special property, we will see that we can introduce a multiplication on G over H, and then the group which is created in this way is called something which is called normal subgroup. It can be factorized, and the resulting group will be called factor group of G over H, factorized by some equivalence. So what we want to do is to define multiplication of two elements of this homogeneous space. And the only candidate for good result is to do it in terms of representatives. That means in this way. So this is the definition. And now we also had, recall the definition that LG1 acting on G2 was the same, G1, G2. And here we checked the consistency of this recipe with respect to the freedom inside these brackets. And we came to conclusion that this is okay, that for any subgroup, this is well-defined formula for any H. Any H works. Now we will do the check of consistency here, whether it is well-defined. What is the danger here? That if you choose other representatives here, for example, G1, H1, and here other representative which is nothing but this, what we need, that it is also other representative of GH, G2, so with some H3. So if this is true, also this should be true, because this is the property of the brackets. So now let's multiply GH, H1 here with G2, H2. So let's multiply here other representatives, And the question is whether it is the same like when we multiply just original representatives modulo some H3 on the right-hand side. This is the question. Because here the rule is, if you want to multiply these equivalence classes, multiply just the representatives and then take class. Here we say that, okay, we multiply the representatives, but other representatives. And if we obtain this result, it gives the same class like here. Yes, because it is just H3. And now we should play with it a little bit. So we can cancel this by G1 H2 minus 1. And what else? You can play a little bit yourself. Some multiplication of something from right and something from left. I will not do it instead of you. And check that the property is that if you make this, you obtain this. Now I will explain what should you obtain. Just I started that cancel this and then do some computation. What does it mean this? That if you take any element from H and make conjugation of this H by any G, you will obtain some other H in principle. So if you conjugate any element from the subgroup, you should also you should obtain element of the subgroup again, which is in general not true. Yes? I already draw the picture that if you have some H here is E, then the conjugated subgroup is in general different subgroup. It is isomorphic to H, but it is a different subgroup. I will give you an example of some computation, which is, I don't remember the number of this exercise, but let H be rotation by alpha along some n. So take SO3. It is the most general element, but now take n fixed. So it is rotation around fixed axis. So it is some SO2 inside SO3. So, sorry, I will write it SO2 as a subgroup of SO3. So this will be our H, and this will be our G. Then make conjugation that multiply by any element from G. Yes. So by beta M, this alpha n, and the inverse element to this is minus beta with respect to the same m. And if you do the computation, the result is that it is rotation by the same angle, but about different axes. And this different axis is this axis modified by this matrix element, or this matrix, R beta M applied on n. So you have some n, and here is some other other n, which goes by rotation of this n by this group element, general group element. Yes? So one can compute this. Now the question is this SO2 of rotations around fixed axis has this property? And the answer is no, because here is in general not just n. Yes? What gives you all elements of your H is this n. This is fixed, and alpha is variable. Yes? So this is important that it is fixed. It is not completely trivial to compute it, but not very easy. It is one exercise in the book. Perhaps it is even in offer for recitations. I'm not sure, but it seems to me. I forgot. Of course, with some hint that how to prove it. So we see that those SO2, that rotations about fixed axis, it is some subgroup in the group of all rotations, and it doesn't fulfill this property. If some subgroups fulfill this property, they are called normal or invariant. So it is the property of this H, yes, of this subgroup. Now, when subgroups are normal, there are many cases which they are normal. And I just put one case which they are not normal or invariant. By the way, why invariant? Because they are invariant with respect to conjugation. So this name is that invariant with respect to conjugation. And why they are normal, I don't know, but for some reason. So important thing is that in order that G over H is a homogeneous space, H is arbitrary subgroup. In order that G over H can be defined a group structure, H cannot be arbitrary, but it should be normal or invariant. But whenever you have normal subgroup somewhere, you can construct G over H, and you are sure that your G over H is not only homogeneous space, but it is also a group itself. And, by the way, this fact actually says that this pi is a homomorphism of this group and this group. Now, what are typical situations where you can find subgroups which are normal? So the first big class is when we have commutative or abelian groups. Yes, if we have the property G1, G2 equals G2, G1, that any two group elements commute with respect to this multiplication, it is called commutative group or abelian group by Abel. And now, because of this property, Ig of H is GH G minus 1 equals G minus 1. H equals H. So it is trivial in this case that this subgroup is isomorphic, not only isomorphic, but equal to the original one after conjugation. That if you conjugate any element, it remains there. So the complete subgroup remains. So that's why IGH is H. By the way, this means, it was already written, that if you apply Ig on H, it can be some other H, yes, in general, in order that the subgroup is normal. It doesn't mean that it is the same H. So it is not, here we do not mean that Ig is identity. Yes? It is some bijection within the H, that if you apply Ig on all elements of G, you obtain all elements of G, of all elements of H, sorry, but not the same ones in general. There are some bijectively mapped. So this is important, that in principle it is not the same, but here, for the abelian group, it is the same, because Ig of H is exactly the same H, so it is even more strong like that, yes? And now, I will go to one theorem, which is called homomorphism theorem, which we, in the proof of which we will see that there are also other interesting classes of normal subgroups. So imagine that we have one group G and a homomorphism to any other group G tilde. And this is homomorphism. Then, first, we can write here that there is image of F, which is a subgroup. When F is homomorphism, that there is a canonical subgroup of G tilde, which is given by elements who came from G. In general, it can be like that, that here is our image of F, and there are some other elements which are not in the image. Yes? And there is one subgroup which is inside the right group. And there is one subgroup which is inside the left group. It is a subgroup of G, and G is from the kernel of F if Fg is E tilde. So here somewhere you have E tilde, it is unit element of the second group. And now here is unit element of the first group. And now here we have some subgroup, kernel of F, which maps to unit element. We can easily check that they are subgroups, both kernel and image of this. For example, the question is kernel a subgroup? So imagine that G1 is from the kernel and G2 is from the kernel. Then the question is whether G1, G2 is from the kernel. The question is whether G1, G2 is mapped to this E. So because it is homomorphism, it is Fg1, Fg2. Now G1 is from the kernel, so it is E. This also is from the kernel by assumption. It is again E, so it is E, and it is E. So also the product is in the kernel. But now, so let's call this kernel H. Now the question is whether it is only a subgroup or it is a normal subgroup. And the claim is that it is the stronger version, that it is a normal subgroup. So the question is that if we have this product, and this is from the kernel, whether this is again from the kernel. So if you have something from the kernel of your homomorphism and you conjugate it by any element, not just H, other H, but arbitrary G, whether it is still in the kernel. So we should compute where it goes by F. So because it is homomorphism, it works like that. Because H is from the kernel, it is E. That means it disappears. And if it is not there, Fg minus 1 is then Fg minus 1, because it is again homomorphism. That means it is F of E, and it is E tilde, because always for homomorphism, if you map unit element, you obtain unit element in the second group. Yes? So what we showed that because it goes to E tilde, this element, it is from the kernel again. So we see that if you want to find some machinery for creating normal subgroups, they are kernels of any homomorphism. Everywhere you have some homomorphism, one group to another group, if you compute its kernel, it is a normal subgroup. And you can check in the same way. No, it is not important. Yes, ImF is also a subgroup. It is enough for us. But now, because the kernel is a subgroup here, we can construct G over H with projection, and we know that this is a group because kernel of F is a normal subgroup. So we can construct G over H and have the standard formula for multiplication of classes. Now we can introduce mapping here called F hat, and the claim is that this is an isomorphism. So F is homomorphism, and F hat is an isomorphism. What is the formula for this F? Remember that this pi is this map. That's by definition. So if you want to define this F, its arguments are elements of G over Kf, so such objects. And now, from the diagram, it is more or less clear that this and this should be this. So if the diagram is commutative, then this is this element from the image of F. So let's introduce this mapping by this formula. First, check that it is a well-defined mapping. What should be checked? That this class is not only given by F by G, but also by GH. So you can put inside, instead of G here, GH. So if you put GH here, and it doesn't work with GH here also, so if we will obtain something else, that what about GH here? because of the homomorphism, it is this, but because H is kernel, yes, where is? So f of H is E tilde. So the right-hand side is insensitive of other representative. The left-hand side is insensitive of the choice of representatives. So it is well-defined mapping. And it is now completely trivial to prove that it is bijection, it is homomorphism. Yes. So the proof is, if you have already this formula, and just the question, the proof that this formula defines a bijection and it defines a homomorphism, it is very, very easy now, yes? And if you do it, you proved that this is an isomorphism, yes? There is a homomorphism. So we can treat this theorem in the sense that whenever you have some homomorphism of groups, you have some derived isomorphism from there of other groups. And what are these two other groups? That if our F is not surjective, then the isomorphism is not of this and this group, but just the image, which is smaller. And here, if there is a non-trivial kernel, the isomorphism is not of G, but of G over the kernel. Yes? So you can do two things, or one thing on the left-hand side, one thing on the right-hand side. On the left-hand side, you should make factorization with respect to the kernel. On the right-hand side, you should just take an image of F not complete G tilde in general. And when you do these two steps, you have some isomorphism of this group. So let's have an example. So let's have a look on this as once again as a machine to construct isomorphisms from homomorphisms. Whenever you invent some homomorphism, you can compute the resulting isomorphism from this theorem. So for example, there are several examples in the book for just be able to do the work. Where are these examples? I will write you 13 to 13. You will see several examples, I think 6 of them or 5. So for example, we have this mapping. A goes to determinant of A. We already studied it several times. It is what? It can be treated as a homomorphism from GL and R to GL1R. It can be also treated as a representation of GL and R as a homomorphism and so on. So let's treat it now as a homomorphism of these two groups. So it is our F. Now we want to find what is kernel of this that and what is image of this that. This kernel should be some subgroup of GL and R, and this image should be some subgroup of GL1R. So let's start with this image group. If you take all matrix elements from GL and R and compute determinant, you can obtain any non-zero number. Yes? You have GL and R matrix for any number backwards. So it is the complete group. It is surjective, if in our case, that here are non-zero numbers, nothing more. And multiplication is multiplication of numbers. So we see that it is the complete group, GL1R. So the image of F is the same like G tilde in our case. But what is the kernel? Here, the unit element in this group is number 1. So we should find matrices which have determinant number 1. So there is a subgroup of all GLNR matrices with determinant 1, and it has even a name that this is SLNR. So what we can write that GLNR over normal subgroup SLNR is a group isomorphic to GL1R. You have several examples like that. You just your task is to find kernel, to find image, and to write the corresponding result. For example, there is, just to mention, I will not compute it, that you have a formula that x goes to logarithm of x, and it can be treated as some homomorphism. You can either think it over, it is the best way, or have a look that what group here, what group here. You know the basic property of logarithm, that logarithm of product is the sum of logarithms, so it says something, that what two groups are there. And then you can compute kernel, image, and so on, and to write something like here. And also quite interesting and important example is for group which is not Lie group. Here, in majority Lie groups so the groups were Lie groups, but if G is Z with respect to plus, yes, and we can treat, for example, H, something which is called, say, 3Z. What is it? It is a subgroup of elements that 3 times any integer. So here elements are 0, 3, 6, and so on, and -3 and -6 and so on. It can be done for any n, for example 2, it will be 0, 2, and so on. So first, check that this is a subgroup, it is easy. Then it is a normal subgroup because the group is commutative. Yes, so this is commutative for abelian. And it is discrete, yes? So not Lie group. And you can compute what is Z over 3Z. So what fiber bundle we obtain? That all Z's now are in 3 fibers. Here will be 0, 3, 6, -3, -6, and so on. It is 1 fiber. It is directly this H. Then you have 1, 4, 7, -2, -5, and so on. And then it will be, it is what? It is 1z, left coset 1z. This is left coset 0z. It is directly, yes, it is directly this H. And here is a coset 2, 5, 8, and so on, minus 1, minus 4, and so on. And here, this is the group, yes, it is G. And what is G over H? In our case, it is the class of this, the class of this, and the class of this. So G over H has just 3 elements, this group. Here are these 3 elements of this group, and the elements of the complete group Z are divided to 3 left cosets, which are in this fiber bundle over your space G over H. And notice that these fibers are discrete here. Yes? So fiber bundles can be also treated as discrete objects. It is not very often done, but it can be done. And our fiber bundles, which are most interesting in theoretical physics, are usually composed of manifolds. Yes, that this is called, in general, the total space. This is called the base, and both total space and base are manifolds usually. But here is an example for this construction when you have discrete fibers. And this discreteness comes also in when we have manifolds. So sometimes happens that you do this construction, you will have a homomorphism with this funny property, and we will do it in detail, one example, next lecture, the last one. But just several ideas today to be prepared of what will happen there. That sometimes we will have G2, this homomorphism, which will be surjective, and kernel of this F will be discrete. This is the most important point. So we have no complication with image of F. It will be, oh, it is here, okay, directly like that. And here we have this projection to G over kernel of F and isomorphism here. But interestingly, that sometimes it comes that you can have Lie groups, but if you compute the kernel of some homomorphism, you can obtain discrete group. So this is now sometimes. Now, imagine that this group has just 2 or 3 elements, 2 elements. We will have important example with 2 elements kernel. So what happens now to our general picture? Our general picture again is like that. That this is typically here is a manifold, and there is also a manifold, and here GH is a manifold. So everything is from differential geometry. You have the complete manifold, these left cosets are manifold, the vector space is manifold, and so on. But now, if this kernel of F is just two-point group, so it is some element, group element which is unit, and some other element. So what happens? That this fiber is some G and all other G's which are multiplication of G by the element of this subgroup. Yes? But now the subgroup has only two elements, so this fiber consists of just two elements. Here is just G and GA. It is G equals GE, GE and GA. And here is the class of G. So this is our G over H, and here is our G. But over this G here, we will only have 2 points. Something here, and no line between, yes? So the fiber consists of just 2 points. But it is not, it is over any element down. So here is some element here. Oh, sorry, the element is here. But you have also here some element, and again, just 2 points over it. For example, element E, the class of E. So we have a point E and point EA, which is A. Here is just the subgroup. Here is our H, and here is our GH. And if you make some domain which is all elements near this G, for example, something like here. Also, over each element here will be just 2 elements, so we will have something like this and this. So over this domain in G over H, you have 2 similar domains on this group G. One is vicinity of G and one is vicinity of GH. Yes? And both of them project by P. So all elements from here project to elements from here, and all elements from here also project to these. Yes? Because all elements from, for example, such strip in general project here in general. So instead of this strip, we have just 2 domains here. This is important. Something like this is called covering. And if there are just 2 elements projecting down, it is called 2-sheet covering. In general, covering can be n sheets, that if you have n pre-images above any point down, with respect to P, it is called n-sheet covering. Oh, it already doesn't make sense. It is already finished, but I made back time. I made back time 31, now is 30. So I will stop just now and I will finish it next lecture, the last one, next one. So I will finish some general treatment a little bit, and then I do in detail some 2-sheet covering of some one group over other group, which is very important for physics. Maybe you know that there exists something SU2 and SO3, and I will do it in detail how it works, this 2-sheet covering for these 2 groups, which is quite interesting, important for physics to know. So thank you for today.